Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video, we defined a method called block normalization, which essentially computed the normalized gradient magnitudes for 2x2 spatial blocks. So essentially, here what we did was to compute the unoriented gradients by adding both positive and negative gradients, resulting in 9 unoriented channels. So these 9 channels were concatenated right here, were concatenated with the previous essentially 18 oriented gradients. Okay, so in this case these cells, these oriented gradients, were concatenated with the gradients that we just computed above, the essentially unoriented, and resulting in 27 channels. Okay, so essentially that is what we did in the last video. What are we going to do in this one? Well, we are going to essentially define the forward method, arguably the most important part of a network. So we are going to essentially set it up. Okay, and how are we going to do that? Well, we just simply we are going to recapitulate, right? We're going to review the content that we've been going through so far and essentially pack it all together. Okay, but just to get started, let's of course import torch, and we're going to of course define the number of orientations and the cell size. Remember that the number of orientations in this particular problem, this particular practical, it's always been 9. Yeah, and the cell size actually originally is 8, but here to simplify things we set it to be equal to 4. And what else? Well, we need to initialize, we need to introduce a random tensor to basically pass through our whole net, yeah, as we've been doing so far. And remember that this tensor is going to have a shape of number of the batch size, yeah, n, the color channels, and the height and the width of the say sample image, yeah. And this will be our input in the the input for the forward method, yeah. So let's define this tensor to be just a random tensor, so torch.random, and it's going to have the following shape. Let's just set it to be just with one batch size, as we have been doing so far. We're gonna have a 3-color channel with a 4x4 pixel distribution. Okay, very simple. And so yeah, just to visualize, let me print it out. So input for the forward pass is going to be random tensor. Great. Okay, so now what? Well, now we are going to start defining the forward method. So this forward method is going to take these random tensor, which remember represents an image. Okay, an image that has the dimensions of batch size, color channel, the height, and the width. So in this case, well, I don't have to call it the same way, but anyways, forward. And how are we going to start? Well, we're going to kick off with the result, the output of compute-oriented gradients. Okay, remember that compute-oriented gradients essentially got for us two elements. It got for us the actual oriented gradients. Okay, let's actually have a look at that. Okay, so if we go back to what we've been doing so far, we define, yeah, exactly right here, the compute oriented gradients, which took an image of the shape that I just mentioned and returned the oriented gradients in N2, which, remember, that was the squared magnitude of the gradients. Okay, so remember that oriented gradients essentially meant that we were able to obtain essentially oriented gradients better say, remember that before compute oriented gradients method we had already the gradients. Okay, the gradients that had both magnitude and direction. Okay, and these magnitudes and directions were linked to the rate of change, of basically the magnitude and direction of the rate of change in intensity, okay, at each pixel. All right, that was what we had before coming into compute-oriented gradients. And what did compute-oriented gradients did for us, or do for us essentially? Well, it essentially took, or it quantized these directions, in the sense that the magnitudes were projected onto the closest orientation. Okay, and essentially, yeah, that is what it did for us. Essentially, just to basically classify these magnitudes into basically the closest orientation, okay, of the gradient. But anyways, and how about the squared magnitude of the gradients? Well, essentially this is a scalar, okay, that essentially represented, of course, just the square of the magnitude of the gradients, as the name suggests. Well, okay, so once we have recalled the meaning of these compute-oriented gradients, we are ready to get started with the definition of the forward method. So essentially what we're going to do is to unpack the result of the compute-oriented gradients method. So essentially we're going to say, okay, so oriented gradients, and this squared of the magnitude of the gradients is just and it's going to take the random tensor. Okay, great. So now yeah, I'm gonna put here explicitly that this is going to unpack the output of the oriented gradients. Also unpack the output of the compute gradient method. Okay, so great. Now what we're gonna do is to just print the shape, because we want to always be aware of the different shapes of our objects. Okay, so in order to do that, well, just let me write a print statement. Yeah, so print, this is going to be the shape of oriented gradients, and just right here, Okay, and same story with the squared magnitude of the gradients. Okay, so okay. And here and 2. Okay, and let me just call the function so far, because I want to also discuss as we go through the different shapes. So random tensor. Well, of course, we need to rerun the previous code that we wrote. So essentially, I'm gonna rerun the different methods that we essentially discussed in the previous videos. And let's start again. Oops, compute-oriented gradients is not above. No, it's not above. Okay, so I need to go way back to over 3.9. Yeah, yeah, right here should be fine. Well, we're going to also need to run angular binning, but yeah, let's go step by step. So I just ran again the compute-oriented gradients method. Okay, fantastic. Now it's working. So now here we have the input tensor, which has the shape of 1, 3, 4, 4, and here's the output shape of the compute-oriented gradients, more specifically of the oriented gradients computation, and we have these 18, 4, and 4. So why is this? Why are we having the these dimensions, right? Well, as you can see, the spatial dimensions have been basically untouched, but what happened is that we went from an input of 3 channels to 18, right? And why is that? Well, because we started with 9 number of orientations, right? And what these oriented gradients contain are essentially both positive and negative orientations. Okay, so because remember that this 9 number of orientations is by default unsigned, in the sense that it is not taking into account the direction, okay, of the gradient, but we want to do so in the compute-oriented gradients. That is why we multiply by 2. We multiply by 2 these 9 in order to obtain both positive and negative contributions, okay? And that is why we get these 18, right? Fantastic. So that's clear. Now let's move to the shape of the square-oriented gradient. So essentially, the main difference is that, okay, we get 1, and that is of course because we're dealing with scalar magnitude, okay? That meaning that these essentially quantity does not contain orientation information, okay? That is why we just have 1. Great. Now that we perfectly understand the output of compute-oriented gradients, let's move on. Let's move on, because all we did was to unpack. So now what we're going to do is to essentially also include the output of the angular binning function. Okay, so because remember that what that did for us, this angular binning, was to take the projections, because remember that what oriented so this compute oriented gradients did was to project the gradients, okay, into the closest orientations, okay, and then it came after that angular binning, which what it did was to take these gradient projections obtained by the compute oriented gradients and smoothly distribute them into discrete bins, all right, and remember that the number of bins was equal to the number of orientations times 2, because again we are taking into account both positive and negative orientations thanks to the introduction of compute oriented gradients, okay? But yeah, that's understood. So now we are going to include that. So oriented, and remember that the output of angular binning was known as histograms, okay? Oriented histograms. So oriented histograms is going to be equal to angular binning, okay? And this angular binning, remember that what it took, okay, let's have a look. Yeah, it took essentially the two objects that we just unpacked, and so all we need to do is to input them here, essentially. So that is our oriented gradients and the magnitudes, okay? Fantastic. So now what we can do too is to print the shape of it, because again it's really important to understand why the shape of our tensor changes as it goes through our forward method, regardless of the type of the network that you're working with. You always need to be very careful with the shape of your tensors as they go through the forward pass, okay? So then the shape of oriented histograms okay, and we're gonna take this. Fantastic. Of course, we need to rerun the angular binning. With what? Yeah, it's here, 3.10. And now let's do it again. Fantastic. So now what happened? Well, with the angular binning, we are taking we are having as channels number of orientations times 2 as well, because essentially what we're doing is taking every gradient projection and classifying it or smoothly distributing it into discrete bins, and as I said, there are as many bins as number of orientations times 2, okay? That is why we also get 18, because there's going to be 1 bin per essentially oriented gradient, okay? Fantastic. So now what can we do? What can we do after this once we have these gradient projections distributed into bins? Yeah, well, so now what we're going to do is to aggregate these gradients, okay, and we're going to do it both horizontally and vertically, okay? And so let's start by aggregating in the horizontal direction, okay? And how did we do that? Well, with the pool U layer. Remember that we defined the pool U, and essentially what we're going to do is the following. So we're just going to store the result of aggregating our oriented histograms in the horizontal direction. So we need to pass the oriented histograms through the pool U layer. Okay, so these oriented histograms, and also important to check the shape here. So shape of oriented histograms after passing through pool U. Okay. Great. And we're gonna have, yeah, let's have a look. Let's have a look. Let's think about this. Well, also pool U. Let's think about this. Okay, that's why. I mean, that was strange, because why are we getting the same shape? Of course, because I didn't change the naming here. Okay, so fantastic. Yeah, now it's makes more sense. As you can see, the only dimension that it changed was this last dimension, which corresponds to the width. Okay, the width of the image, and it went from 4 to 1. And essentially what happened is that we aggregated all the information in the horizontal direction, that meaning the width of the image, and it went from 4 to 1. Okay, fantastic. So now what we want to do is to do exactly the same idea, apply the same idea of aggregation, but now in the vertical direction, that meaning the height of the image. All right, so that is exactly what we're going to do. So we apply the same idea, but in the, so to pool V, essentially representing the vertical direction, aggregation, and print this shape of oriented histogram after passing through pool V. Yeah, this should work out. Let's have a look. Great. So essentially what happened is, well, we now aggregated in the vertical direction, in the height of the image. So essentially we end up with a 1-1 shape for the image, as we are aggregating everything to one dimension. Yeah, or basically reducing or collapsing all the information into one, yeah, instead of the original height and width dimensions. Okay, so now once we have done that, what is next? Well, we want to apply the block normalization. Okay, and remember, we just talked about it in the beginning of this video, and essentially we are going to apply it now, apply it at this stage. Okay, so what we're going to do is we're going to call this result as HOG, okay, because this is going to be the actual histogram of oriented gradients. Okay, the result of applying say this series of operations. Yeah, and the series of operations end with the block normalization. And use cells to pass through. Well, remember, we need to run again the block normalization method. Okay, and now also let me print the shape. So the shape of, say, aggregated oriented histograms after being block normalized. Okay. Okay, let's have a look at this. Oh wow, what happened? Well, have a look at this. We went from 18 to 27, and yeah, it's natural to ask why, right? Why this sudden increase in channels? Yeah, well, because remember what we mentioned in the beginning of this video. Yeah, so essentially saw here that there was a concatenation, yeah, here, right here, where we put on both unoriented and oriented gradients together. All right, so essentially what happened is that we took the 18 oriented gradients and concatenated them with these 9 unoriented gradients. Okay, that is why we have 18 plus 9, 27 channels. All right, fantastic. So after these block normalization, essentially, yeah, we are done with the forward pass of our net. Wow, that's an amazing achievement, right? After these pretty long, yeah, net, but yeah, right here. So just let's return the HOG, and yeah, why not? For fun, let's have a look at it. Oh wow, you see, we have this shape of 12711, so a series of 1 numbers in, so there's 1 number per channel for these 27 channels. Yeah, great. So what could we do now? Well, after we have obtained the HOG, remember, this forward method gives us the actual oriented, or the histogram of oriented gradients. Okay, so what do we do with them now? Well, we need to render them. We need to render them to be able to visualize the actual histogram, right? And how can we get started with that? Well, we need to define a method. We need to define a method that is able to render the HOG. Yeah, and this method. So let's go rendering the HOGs, and let's call this method to image. Okay, fantastic. So how can we get started? Well, before anything, let's actually store the result of our forward method. Great. So now let's get started. So let's define to image, and let's input the actual HOG. Yeah. And how do we start with this? Well, remember that as this method aims to basically render the image, there's no need to compute any gradients. Okay, in here there will be no computation of any kind of gradients. That is why we just want to inactivate, yeah, the functionality. So for that we just say okay, no grad. Okay, this is basically saying, okay, within this block, we're not going to compute any kind of gradients, yeah? All right, so what are we going to do now? Well, we're going to compute the so-called weights, okay? And what do I mean with these weights? Well, what we're going to do is to actually collapse all the contributions of the gradients that we've been obtaining so far. Essentially, we are going to collapse the contributions of positive, negative, and unoriented gradients for each of the 9 orientations, okay, into a single channel per orientation, okay? So that is in words. Let's code it out. So weights. So how do we start? Well, we need to keep in mind that by convention, it is usually basically, so conventionally, we see that the positively oriented gradients are stored first. So because remember, we're going to have 27 channels, yeah? We're going to have 27 channels, and by convention, we're going to have the first 9 of these 27 are going to be the positively oriented ones. Then the following 9 are going to be the negative oriented gradients, yeah? And the final 9 are going to be the unoriented gradients. Again, this is the convention, this order, right? And we're just going to follow that, yeah? So it's going to be, so how do we code that? Well, we're going to say, well, we don't want to touch the, we just want to carry all the batch numbers, yeah, the batch size, and we just want to take the first 9, yeah, the first 9 channels. So for that we say, okay, so the first 9 is up to number of orientations, which is equal to 9, and the rest we also want to carry with us, yeah, carry over with us. Okay, so this is going to be added, yeah, it's going to be added. And let me also add a comment here that these are the positive oriented gradients, okay? These first 9 channels correspond to the positive oriented gradients. Great, and we are going to do the same, okay? We're going to do the same. So this, we're going to carry on. We're going to carry on with this idea, yeah? And so now we want to take the next 9 channels. So how do we do that? Well, we need to slice from 9 to the next 9, which of course are going to be number of orientation times 2. Okay. Fantastic. These are the negative oriented gradients, and well, remember that this is a 9, and we're going from a 9 to the next 9, yeah? So from 9 till 18, that is why we multiply by 2 here, yeah? Fantastic. So now there's one left. There's one block left, and that is the last 9 channels of the total of 27, yeah? So to do that, we just take the last, so from 18, the channel number 18, up to the end, yeah? Great. Okay, fantastic. So now we have the weights. These are the weights. So what is next? Well, next is to have a look at the shape. Okay, let's do this. Okay, weights. And let's have a look. So image, and we're going to pass through the HOG, yeah? Let's see. Okay, invalid syntax. Why? Let me think. What's going on? Okay, yeah, because I added an extra plus. Okay, makes sense. So the shape of the weight, well, remember, we want the shape, not the actual contents. Oh, you see, we went from 27, all these 27 collapsed to 9. And again, this is the reason, because we are collapsing all the information. So the information stored within these 27 channels, we are collapsing it into just 9. Okay, as expected. Okay, now what is next? Well, next, once we have collapsed all this information into 9 channels, we're going to render the HOG. Yeah. So remember that we defined in previous videos these render layer. So we're just going to apply it. So we're going to say, okay, image equals render, and we're going to pass the weights through the render. Yeah. Okay. So let me now have a look at the shape. So shape of the output is going to be, let's have a look. Oh wow, what happened? So you see that, well, let me put here a space, it looks nicer. You see that we went, first of all, from 9 channels to 1, and all of a sudden we got 21. So what happened? Well, first of all, we need to remember that in this so in the render layer, let's have a look. Okay, let's go back to where we discussed the render. Actually, it will be easier if I go just to the say well-structured net. Yeah, you see here this render. Okay, this render involved convolutional transpose operation, and remember that yeah, we got this GS, yeah, and this GS was equal to 21 and was the size of the so-called glyph. Okay, and remember that a glyph is just a small visual representation of our data. Okay, it's going to provide a way to say visualize the gradient. Okay, the gradient directions and magnitudes both. Yeah. So that is the meaning of glyph, and we set it to be equal to 21. So essentially what's happening is that the image is being upsampled, okay? It's being upsampled to the size of the glyph that we set up previously, okay? And this upsampling is important. Why? Because we are restoring a spatial resolution, okay? Which is going to be key to be able to identify patterns within our gradient representations. Yeah, fantastic. So now that we understand why we got this 21, basically because we set our glyph to be 21, and that the rendering is essentially upsampling the say 1:1 collapsed image to the size of the glyph. Yeah, and yeah, that is essentially what happened. And also notice that the rendering also collapsed the channel dimension from 9 to 1. So essentially what happened is that all the information that was previously collapsed to 9 channels, now it collapsed to just 1. Okay, and yeah, that is exactly what we observe. So essentially, what is next? Well, next is to pre-process a bit the content of this image, this the output of the render. And what do I mean by that? Well, essentially, we're going to set some boundary values. So what I mean by that is that we're going to identify, okay, what is the minimum value of our weight tensor, and what is our maximum value of the weight tensor, and we are going to clamp the results using those maximum and minimum values. So let me code that out. But first of all, let me have a look at these maximum and minimum values. So what we're going to have is the minimum value of the weight is, and I'm going to take the weight dot min okay, and the maximum value of weight is this weight, well, it's in plural, right? Weights dot max, okay, dot max, and right there we have it. Great, fantastic. So now we have that, and let me visualize. Okay, let's visualize these minimum maximum values. Okay, so you see that the minimum value is 0 and the maximum value is this 1.06. So essentially this is going to limit the output of our rendering. So it's going to with this clamping, we're going to avoid having negative values and values above 1.06 as a result of the rendering process. So let's then apply the clamping to the result of the rendering. So torch.clamp, and as an input, of course, the output of the rendering, and the boundary values, the limitations, the limits are going to be, so the lower boundary is going to be min, and the upper boundary is going to be this one, weight dot max. Great. So now what is next? Well, let's just have a look, because we would expect the shape of these clamping to basically be the same as the shape of the output of the render, because all we're doing is just limiting the maximum and minimum values. So the shape shouldn't change at all, but let's verify that. So shape of output of rendering output after clamping. Okay, and shape. Okay, great. Let's have a look. Indeed, as expected, after clamping, the shape is unaffected. Fantastic. So that is all I wanted to discuss in this video. I hope it is helpful, and I am willing to see you very soon.